Refraction. Refraction is the bending of light as it travels from one medium to another.
Refraction experiment number 1, pencil and glass.
For this experiment, you'll need a pencil and a clear glass filled with water.
Simply place the pencil in the water. As you can see, the pencil appears bent. This phenomenon occurs because the light is bent at the boundary between water and the air around it. If light travels from one transparent medium to another at any angle other than straight, then the light ray changes direction when it meets the boundary.
Refraction experiment number 2, internal reflection.
For the experiment, you will need a pitcher of water, baking soda, a measuring cup to measure the baking soda, a container, a stirring rod, and a laser.
Put your water into the tub. Measure 1/4 of a cup of baking soda.
Just dump it now. Stir it up.
And stir it up. Not quite working.
Alright, that's fine. It's fine. And now you're ready for your experiment. Place the laser towards the bottom of the container. Once you have done so, you will need to turn off the lights and then proceed on to turn on the laser.
As you can see, the light ray is reflected back into the bowl. This is called total internal reflection. This can occur when light attempts to move from a material with a higher index of refraction to one with a lower index of refraction. If the angle of incidence is greater than the critical angle, then the ray is totally reflected at the boundary.
Interference. Interference is the combination of light waves to form a resultant wave. There's two types of interference, constructive interference and destructive interference. Constructive interference is when any types of waves combine to form a resultant wave with an amplitude that is greater than the amplitude of either of the individual component waves. We can show constructive interference by demonstrating an easy additional equation. This is the first wave. And now we're going to draw the second wave. You see that the peaks and valleys match up evenly to form the resultant wave, which I'll draw next. So if we were to add these two waves together, we'd get a wave with much bigger peaks and valleys, which is our resultant wave. This is an example of constructive interference. Destructive interference is when waves combine to form a resultant wave with an amplitude that is less than the amplitude of the larger component. To demonstrate destructive interference, we can do another simple addition equation. This is the first wave. Now I'll draw this second wave with its peaks and valleys aligning opposite with the peaks and valleys of the first wave. The first wave would be a number, a positive number in equation, and the second wave would be a negative number. So it's like you're subtracting them, but you're really adding them. So now the resultant wave would be just a straight line. To show interference, you have two wave sources, source 1 and source 2. They both shoot waves out, creating a ripple effect. The waves get bigger as they get farther away, growing. As the two waves interfere, they create an interference pattern in between. This is the interference pattern the waves create as they combine. The red marker represents where the waves constructively interfere. These spots are also referred to as maximum pressure points. The blue marker represents where waves destructively interfere. Also referred to as minimum pressure points.
Interference can be shown when throwing rocks into a pond. When two rocks are thrown in at the same time, they create ripple effects. These ripple effects cross over each other, forming an interference pattern with constructive interference and destructive interference spots.
Diffraction. Diffraction is the effect of a wave spreading as it passes through an opening or goes around an object. Diffraction can occur with all types of waves, including sound waves, water waves, and electromagnetic waves, such as visible light, X-rays, and radio waves.
Experiment number 3, Young's double slit experiment for diffraction and interference. This experiment was done by Thomas Young in the early 1800s. He shot a light source through two slits and projected it onto a viewing screen. This was done to see if light is a wave or a particle. If light is a particle, Young was expecting a pattern to be shown on the viewing screen, such as the picture above. If light is a wave, Young was expecting a pattern similar to the picture below, where interference occurred, creating light spots and dark spots on the viewing screen. In this experiment, you will need a laser pointer to act as the light source, 3 pieces of lead to act as the 2 slits, and a wall to project your light on. To begin, take your 3 pieces of lead and put them close together, extremely tight, to act as the 2 slits. Then, take your laser and use it as the light source to shine it through the 2 slits. Once you turn on the laser, turn off the lights. As you may notice, the laser has created an abnormal pattern on the wall. This pattern, as you may see in the picture above, is called a diffraction pattern, consisting of many light spots and dark spots across the wall. As you can see in the mock diagram below of the diffraction pattern, the largest and brightest spot in the diagram is called the central maximum. To the left and right of the central maximum, the bright spots are called the secondary maximum. And finally, the dark spots are called the minimum. The bright spots are broken up into orders depending on their location in the diffraction pattern. The central maximum is considered the 0th order. The first secondary maximum to the right and left of the central maximum are considered first order. The orders of the secondary maximum go up as they move further away from the central maximum.